Let knowledge flow like a river, without any hindrance. Don't make it like a stagnant pool. Hello everyone. I'm P.S. Chatterjee, and welcome to my channel. Today, we're diving into Excel for IS 456, single reinforced section and steel percentage with SP16. This is part 1, the first in a series of DIY projects for civil engineering. A tip for new viewers: if you're a civil engineer, I encourage you to watch my other videos related to civil engineering to expand your knowledge. To get the free Excel sheet, please read the description carefully. Many viewers have emailed me directly requesting the free Excel sheet. To receive it, please send an email with your request and leave a comment on the relevant video stating that you've sent an email. This is required. After receiving the file, please acknowledge receipt in the comments section of the video. This helps me and other viewers and reinforces my mission of sharing knowledge freely. I appreciate your cooperation. If you find this video useful, please like, share, comment, and subscribe. During this video's creation, I considered concrete and steel grades outside SP16 tables. Gemini AI clarified that IS 456 formulas are applicable to all grades, and these formulas or structural software can be used. This slide shows the arrangement of reinforcement in a singly reinforced section. On the left, we see the cross-section of a slab. The rectangle represents the concrete. The B indicates the width, and capital D the overall depth. The small d represents the effective depth, measured from the compression face to the centroid of the tension reinforcement. The red dotted line marks the location of the main tension bars. The green box highlights these as tension bars. The distance from the bottom of the slab to the center of the tension bars is labeled the effective cover. The cover label points to the concrete surrounding the reinforcement, providing protection. On the right, we have the cross-section of a beam. Again, B indicates the width and capital D the overall depth, with small d being the effective depth. Similar to the slab, we see the tension bars at the bottom. However, in beams, we also have shear bars, shown in yellow, which are essential for resisting shear forces. Additionally, there are anchorage bars at the top, which help tie the reinforcement together. The effective cover and cover are labeled in the same way as in the slab. Understanding the arrangement of reinforcement is essential for designing structurally sound concrete elements. This slide highlights the key differences in reinforcement layout between slabs and beams, emphasizing the importance of cover, effective depth, and the inclusion of shear and anchorage bars in beams. As we've seen, these diagrams illustrate the strain distribution. It's important to note that, while I've shown the tension bars at the bottom, this is for illustrative purposes. The defining characteristic of a singly reinforced section is that the tension bars are placed within the tension zone of the concrete. This zone varies depending on the loading and support conditions. For example, in a fixed-end beam, the tension zone at the supports is at the top, necessitating top reinforcement at those locations. Next slide. Actual and design strain diagram. In this slide, we see a cross-section of a rectangular beam. The overall depth of this beam is denoted by the capital letter D, the width by the small letter b, and the effective depth, the distance from the top compression fiber of the concrete to the centroid of the reinforcement, is denoted by the small letter d. To the right of the beam cross-section, the first diagram represents the actual strain distribution in concrete under bending moment. While the stress-strain relationship in concrete is nonlinear, especially beyond the elastic range, the strain distribution across the beam section is assumed to be linear, as per IS 456. The line passing through the point where the strain is zero is called the neutral axis. Since strain varies linearly across the section, the stress at this point is also zero. The diagram further to the right represents the simplified, linear strain distribution used for design calculations. This simplified diagram is a representative strain distribution for concrete. The maximum compressive strain in concrete is assumed to be 0.0035, and the strain in the steel reinforcement is 0.87 Fy by ES, plus 0.002. Remember that strain is a dimensionless ratio. Next slide, balanced, under-reinforced and over-reinforced section. Before entering actual design practice, we need to understand the behavior of a singly reinforced section. In reinforced concrete beams, the balance between the concrete and the steel reinforcement is crucial for structural integrity. We categorize beams into three main types based on the amount of steel used: balanced sections, under-reinforced section, and over-reinforced section. While creating a perfectly balanced section is theoretically possible, practical designs focus on under-reinforced sections to ensure safety and ductility. Next, balanced reinforced section. In this reinforced concrete beam section, the actual neutral axis, XU, coincides with the maximum neutral axis, XU max. A balanced section is characterized by the concrete reaching its maximum allowable strain, crushing strain, and the steel reaching its yield strain simultaneously. Next, under-reinforced section. For an under-reinforced section, the actual neutral axis, XU, is located above where the maximum neutral axis, XU max, would be. This is because XU is less in depth than XU max, meaning it's positioned higher in the beam section. In this scenario, we are providing less tensile steel than required for a balanced section. Consequently, the steel reaches its yield stress before the concrete reaches its crushing strength. In this case, the steel reinforcement yields first. This results in a ductile failure, providing a warning before collapse through significant deflection. This is the desired behavior in design. Since we are providing less steel than a balanced section, this type of section is known as an under-reinforced section. Next, over-reinforced section. For an over-reinforced section, the actual neutral axis, XU, is located below where the maximum neutral axis, XU max, would be. This is because XU is greater in depth than XU max, meaning it's positioned lower in the beam section. In this scenario, we are providing more tensile steel than required for a balanced section. Consequently, the concrete reaches its crushing strength before the steel yields. This leads to a sudden and brittle failure of the concrete, with little or no warning. Over-reinforced sections are undesirable because they fail abruptly, without providing the ductile behavior that signals impending collapse. Since we are providing more steel than a balanced section, this type of section is known as an over-reinforced section. In summary, under-reinforced sections are designed to fail by steel yielding, providing a warning, while over-reinforced sections fail by concrete crushing, leading to a sudden and dangerous collapse. Design codes generally prefer under-reinforced sections to ensure safety. When analyzing reinforced concrete beams, we compare the actual neutral axis position, XU, to the maximum, or limiting, neutral axis position, XU max. This comparison is vital for understanding how the beam will behave under load. In the next slides, we are going to reveal the formulas for bending moment. This slide presents the formulas for calculating the minimum percentage of steel reinforcement in a singly reinforced section. As you can see, the heading states formulas for single reinforced section followed by minimum percentage of steel. This highlights the slide's focus on the minimum amount of steel required in concrete design. As per IS 456, 2000, when the yield strength of steel, denoted as Fy, is less than or equal to 250 newtons per square millimeter. In such cases, the minimum percentage of tensile steel, represented as PT, min, is 0.15%. When the yield strength of steel, Fy, exceeds 250 newtons per square millimeter. For this scenario, the minimum percentage of tensile steel, PT, min, is 0.12%. In summary, the minimum percentage of steel reinforcement in a singly reinforced section depends on the yield strength of the steel. Lower yield strengths require a higher minimum percentage of steel. Practical scenario regarding minimum percentage of steel in beam. It's worth noting that in practical beam design, engineers frequently adopt a more conservative approach. While design codes, such as IS 456, specify a minimum reinforcement ratio of 0.12% or 0.15% based on the steel grade, it's common practice to use a minimum of 0.2% for beams, regardless of the steel grade. This difference between code-specified minimums and practical applications isn't a discrepancy in the sense of an error, but rather a deliberate and justifiable adjustment for increased safety, serviceability, and reliability. It reflects a balance between theoretical calculations and the realities of construction and material behavior. If you're interested in a more detailed explanation of this practical adjustment and the reasoning behind it, including specific code clauses and design examples, please leave a comment below saying, "Detail video required on this," and I'll create a dedicated video on the topic. Next, calculation for maximum depth of neutral axis, XU max. This slide details the calculation of the maximum depth of the neutral axis, denoted as XU max, for a singly reinforced section. We begin with the strain diagram for a balanced singly reinforced section. As shown, the diagram consists of two right-angled triangles oriented in opposite directions. From geometric principles, the ratio of the vertical sides of the red and green triangles is equal to the ratio of their corresponding bases. In step 1, we establish this relationship. If we consider the total vertical length to be 1 unit, and the vertical length of the green triangle is XU max, then the vertical length of the red triangle is 1 minus XU max. The base of the red triangle represents the maximum strain in the steel reinforcement, given by 0.87 times Fy, divided by Es, plus 0.002. The base of the green triangle represents the maximum strain in the concrete, which is 0.0035. It's important to remember that strain is a dimensionless ratio. Therefore, we can express the relationship as 1 minus xu max, divided by xu max, equals 0.87 times Fy, divided by Es, plus 0.002, divided by 0.0035. Steps 2, 3, and 4 involve successive algebraic simplifications of this equation. In step 2, we simplify the left-hand side. Step 3 further isolates xu max. Step 4 simplifies the right-hand side. Finally, in step 5, we arrive at the formula for xu max. As highlighted in the green box with the red dotted outline, xu max is equal to 0.0035 times Es, divided by 0.0055 times Es, plus 0.87 times Fy. Next, we will discuss the calculation for total compressive force, Cu max. This diagram illustrates the calculation of the total compressive force, denoted as Cu max, within a concrete beam stress block. The stress block is divided into rectangular and parabolic areas, labeled AR and AP respectively. The base of each area is 0.446 FCK. The total height of these two areas is xu max. The height of the rectangular area AR is 0.416 xu max. The area of the rectangle, AR, is calculated as 0.446 FCK multiplied by 0.416 xu max. Let the height of the parabolic area AP be denoted as A. Then, A equals to xu max minus 0.416 xu max, which simplifies to 0.584 xu max. The area of the parabola, AP, is calculated as 2/3 of 0.446 FCK multiplied by 0.584 xu max. The maximum compressive stress is represented as 0.446 FCK. The depth of the neutral axis, xu max, is a crucial parameter. The total area of the stress block, AS, is obtained by adding AR and AP. This simplifies to 0.36 FCK xu max. Finally, the total compressive force Cu max is determined by multiplying As with the width of the beam, B. This results in the equation Cu max equals 0.36 FCK xu max B. Next, we will discuss the calculation for total tensile force, Tu max. This slide details the calculations for the maximum tensile force, denoted as Tu max, and the limiting moment of resistance, denoted as Mu lim. First, let's examine the calculation of the maximum tensile force, Tu max. As illustrated in this diagram, the total tensile force, Tu max, within the concrete beam stress block for a balanced, singly reinforced section is calculated as Tu max equals Fy by gamma m into Ast, where Fy is the yield stress of the steel reinforcement. Gamma m is the partial factor of safety for steel yield stress, with a value of 1.15. Ast is the total cross-sectional area of the tensile steel reinforcement. Therefore, the design yield stress is Fy by 1.15 equals 0.87 Fy and Tu max equals 0.87 Fy into AST. Now, let's proceed to the calculation of the limiting moment of resistance for the section, mu lim. For a balanced section, the total compressive force Cu max is equal to Tu max. From the diagram, Cu max equals 0.36 FCK x U max B. Therefore, Tu max equals 0.36 FCK x U max B. Let Z represent the distance between Cu max and Tu max. Z equals D minus 0.416 x U max, where D is the effective depth of the section. The limiting moment of resistance, mu lim, can be expressed as mu lim equals Cu max into Z. Substituting the values for Cu max and Z. Mu lim equals 0.36 FCK x U max B into D, 0.416 x U max. By rearranging and simplifying, we obtain mu lim by BD square equals 0.36 FCK x U max by D into 1 minus 0.416 x U max by D. This relationship is highlighted in the green cell with the red dotted border at the bottom of the diagram. Next, we will discuss the calculation for the limiting percentage of steel, PT lim. This slide illustrates the calculation of the limiting percentage of steel, denoted as PT lim. Since Cu max equals Tu max and Cu max equals to 0.36 FCK x U max B, Tu max equals to 0.87 into Fy into AST. Here AST is the total cross-sectional area of steel. AST equals to PT lim into B into D by 100. Here D is the effective depth of the section and B is the width of the section. We can equate Tu max equals to 0.36 FCK x U max into B. Substituting AST as PT lim into B into D by 100 and Tu max. We get 0.36 FCK x U max B equals to 0.87 Fy into PT lim into B into D by 100. Therefore, PT lim equals to 0.36 FCK x U max into 100 by 0.87 Fy into D. Next, in practical engineering design scenarios, it is frequently necessary to ascertain the actual moment of resistance, mu by BD square, the depth of the neutral axis, xu by D, and the requisite percentage of tensile reinforcement, PT required, for a specified set of design loads and material properties. This slide delineates the transition from theoretical limits to these applied calculations. This slide explains how to find the percentage of steel required, denoted as PTREQ, and the ratio of the neutral axis depth to the effective depth, denoted as XU by D. Given that compressive force Cu equals tensile force Tu, we have Cu equals to 0.36 FCK into XU into B. Tu equals to 0.87 into Fy into AST, where AST equals to PT required into B into D by 100. Equating Cu and Tu. 0.36 FCK into XU into B equals to 0.87 Fy into PT required into B into D by 100. From this, the ratio XU by D is expressed as XU by D equals to PT required into 0.87 Fy by 100 into 0.36 FCK. The moment of resistance mu is given by mu equals to Tu into Z, where Z equals to D minus 0.416 XU. Substituting for Tu and Z, mu equals to 0.87 Fy into PT required into B into D by 100 into D minus 0.416 XU. Finally, rearranging to solve for PT required. PT required equals 100 into mu by B into D square into 0.87 Fy into 1 to 0.416 XU by D. Next, the boundary conditions for the design of a singly reinforced section will be discussed. This slide summarizes the key design criteria for singly reinforced sections under bending moment. We've covered 3 essential checks in this video. Design Criterion 01. The first criterion ensures that the depth of the neutral axis, XU, remains within acceptable limits. We compare the ratio of XU to the effective depth D with the maximum allowable ratio, XU max divided by D. This ensures ductile failure. XU is the calculated depth of the neutral axis, in millimeters. XU max is the maximum allowable depth of the neutral axis, in millimeters. D is the effective depth of the section, in millimeters. Design Criterion 02. The second criterion focuses on the moment capacity. We check that the calculated factored bending moment, mu, is less than or equal to the limiting factored bending moment, mu lim. This ensures the section can resist the applied bending moment. Mu is the calculated factored bending moment, in kilonewton meters. Mu lim is the limiting factored bending moment, in kilonewton meters. Design Criterion 03. The final criterion addresses the amount of steel reinforcement. We ensure that the provided percentage of steel, PT, falls within the minimum and maximum allowable percentages, PT min and PT lim respectively. This ensures adequate reinforcement for strength and ductility. PT min is the minimum percentage of steel. PT is the provided percentage of steel. PT lim is the maximum percentage of allowable steel. These 3 criteria are essential for ensuring the safe and effective design of singly reinforced concrete sections under bending. And that concludes part 1 of our journey into Excel for IS 456, single reinforced section and steel percentage with SP16. Next week, I'll upload part 2, where we'll apply all the formulas we've discussed today. I hope you found this tutorial insightful and enjoyable. If you found this video helpful, please give it a like, share it with your colleagues, and subscribe to the channel. Your feedback and questions are always welcome in the comments below. Let's keep learning and growing together.